Let me take this off. This is section 8.6 part 2. So I have an extra example. So we have dx dt equals x plus y. dy dt equals negative 2x minus y. Okay, so let's write our system of equations in matrix form. So we have x prime equals, what are the coefficients? What's the matrix A?
1.
Very good. Times x, yes? Okay, so step 1, we're going to find our eigenvalues. So we need determinant of a minus lambda I, set it equal to 0. So we're going to have 1 minus lambda, 1, negative 2, negative 1 minus lambda equals 0. So what do we get? 1 minus lambda times negative 1 minus lambda plus 2 is 0. Multiply it out, so negative 1 minus lambda plus lambda squared plus 2 is 0. Good? Okay, so then this cleans up. What are we left with? So lambda equals plus or minus I. So those are our eigenvalues, okay? Now, really we only have to find eigenvector for one of them, right? Because your eigenvalues, when they're complex, they come in conjugate pairs. And the eigenvectors that correspond to them are also complex conjugates. So once you get one, you have the other one automatically. So I usually just deal with the positive one first. Let's be positive people. So lambda 1 is I. So let's go ahead, let's find the eigenvector. So we have 1 minus I, 1, negative 2, negative 1 minus I. So what you do here to get the eigenvector, you want to have a real constant, right, as your pivot in the top left. So since we have that complex number up there, just interchange your two rows. That's always going to be your first move. Otherwise, you're not going to be able to get, well, it's more difficult to get a real number. You'd have to multiply by the complex conjugate. I don't think it's worth doing that. So I'm going to interchange row 1 and row 2. Okay. So then what do we have? We'll have negative 2, negative 1 minus I, 1 minus I, 1. Okay, so let's focus. We need to make this a positive 1. So what should we do? Good. So negative 1/2 row 1 is my new row 1. So we're going to have 1. This will become 1/2 plus 1/2 I, yes? And then this is just going to stay right now, 1 minus I and 1. So now I need to make this entry a 0 using the pivot in row 1. So I'm going to multiply row 1 by the additive inverse of 1 minus I, which would be negative 1 plus I times row 1 plus row 2 is my new row 2. Are we okay so far? Okay. So then row 1's not changing. 1, 1/2 plus 1/2 I. This is going to become 0. And then, I mean, you can take it for granted. What does that bottom entry have to be in row 2, column 2? It has to be 0, right? But let's make sure, especially because when we do the 3 by 3 case, you have to actually figure out what it's going to be, all right? So from here, if I take negative 1 plus I times row 1 times this entry here, which is 1/2 plus 1/2 I, and I'm going to add it to row 2, which currently has a 1, that's going to give me the new entry in row 2. So what's the slickest way to multiply this out? I wouldn't start foiling. No. You see how you could take a 1/2 out of 1/2 plus 1/2 I? Do that. Then you have negative 1 plus I times 1 plus I plus 1. Yes? So what is this going to give us if we multiplied it out? Those are conjugate pairs. Negative 1. And then plus I squared. Good. Plus 1. So yeah, this is negative 2 times 1/2 plus 1, which is indeed 0, as we suspected, right? We got a 0. Good? You guys okay? Okay, so then from here, we're ready to go. Maybe take the time to write out this next step in case you're jumbling up how to write the eigenvector. So this times u1, u2 gives me 0, 0. So then we have from the first row, u1 plus 1/2 times 1 plus I u2 is 0, which means u1 equals negative 1/2 times 1 plus I u2. So then if you're going to write this as a vector, we have negative 1/2 times 1 plus I times u2 and then 1. But we don't want to have any fractions in there, so I'm going to multiply everything through by 2. So for k1, for my final eigenvector, I'll have negative 1 minus I and then positive 2 down here. Are we good? Okay, so that corresponds with lambda 1 equaling I. Now you can repeat the whole process again, but I feel confident we didn't mess up. So since lambda 2 is negative I, what would the vector k2 be? Good. Negative 1 plus I and 2. Okay, good. All right, now here's the issue. We cannot report our final answers in this form because looking at the original differential equation, all of the coefficients were real constants. Real. We didn't have any complex numbers. So the solution to this differential equation lives in real matrix space, not complex. So we're going to use Euler's identity to rewrite the imaginary answers in terms of sines and cosines, and then extract our real valued vectors from there that we'll use to construct our solution, okay? Think back when we were in chapter 4 and we were solving equations and you had and the characteristic equation say it had complex roots, right? How did you write your answer when m was imaginary? Did you leave i's? Did you write e to the I, whatever the root was? No, we used Euler's identity, right? So we're going to do the same thing right now. So let me remind you, if you have e to the it, you write it as cosine t plus I sine t. So basically for this first term here, where lambda 1 is I, and then we have k1, let's just form x1 for a hot second. So x1 would be e to the it times negative 1 minus I and 2, right? Okay, so I'm going to replace e to the it with cosine t plus I sine t, and then this gets multiplied by negative 1 minus I and 2. So you're going to multiply it all out. You're going to have to distribute. So then this is going to be, let's see, I'm going to take cosine t times negative 1, so that's negative cosine t times negative I. Let me write minus I cosine t minus I sine t, and then plus sine t. Good? And then the second row, I'm just going to multiply cosine t plus I sine t by 2. So just 2 cosine t plus 2I sine t. And then what we're going to do is separate the imaginary part from the real part. Up to here, you guys need a recap or anything? We're good? Okay. So the real part, let's see, no complex, no imaginary part there, no imaginary part there. So I'm going to write x1 as this vector here is real, sine t minus cosine t, and then 2 cosine t, plus, here's the imaginary part, negative cosine t minus sine t, and then 2 sine t. Now I want you to put this on hold, okay? So you put it on the little simmer burner in the back of the stove. Just leave it alone for a minute, okay? Good? Now let me show you, we're going to do the same thing for x2. So x2, it would be e to the negative I times t, and then where was k2? There it is, right? Negative 1 plus I and 2. Okay, so same thing. We're going to replace e to the negative it with what? Okay, maybe off to the side, let me help you guys. This would be cosine negative t plus I sine negative t, right? Since we have a minus sign in the exponent this time. Very good. So cosine's even, so the negative gets absorbed. Sine is odd, so then it's minus I sine t. Good, Labib, look at that. Okay, so then I'm going to have cosine t minus I sine t times the vector negative 1 plus I 2. So let's multiply it out the same way, and then we're going to separate the real part from the imaginary part, just like we did with x1. So in the first row, let's see, it'll be negative cosine t plus I sine t plus I cosine t minus I squared sine t, but what will that simplify to? I squared is? So now it'll be positive sine t, right? And then second row is just going to be 2 cosine t minus 2I sine t. Okay? Are we okay? Yeah. Okay, then let's separate real from imaginary. So this is real, real, real. So x2 is sine t minus cosine t, 2 cosine t, plus I times sine t plus cosine t, negative 2 sine t. How very curious. How do these compare with what I told you to put on hold for the real and imaginary part for x1? They're basically scalar multiples. Like the real part is the same. Do you see that? Yeah. And then the imaginary part is just multiplied by a scalar. So these are scalar multiples of the previous. Okay. Now let's think back. That means you never have to go through the process of extracting the real and imaginary part from the conjugate eigenvalue eigenvector. It will always be scalar multiples of the real imaginary part of the original one that you found. Okay? So when you have eigenvectors and eigenvalues that are conjugates, complex conjugates, you just need to extract the real and imaginary part from one of them, and then the other one, it will just be the same thing. Repeated again, okay? And then you get, since you have a real part and an imaginary part, that gives you 2 vectors right there. So that's enough for each of them. Yeah, Jacob?
Is it negative though?
It's fine because it's a scalar multiple. So let's think about, like, our superposition principle says you take a linear combination of solutions and you have a solution. Mm-hmm. So it'll just get absorbed in C.
It's still in this, like, the same space.
Yeah,
So,
exactly.
So you're saying same thing with, like, finding the eigenvector in the beginning, you don't have to really do the other one.
Don't do the other one. Yeah. And then these are the vectors that we're going to use. You don't even have to use I anymore, right? So what happens is, did you still have a question, Labib, before I?
Basically, just like after everything's done, it's going to be like the K is the same, everything's just, well, the K is different, right? But like,
Yeah, I mean, and then the book sometimes calls it like C4, C5. I don't care. Just do C1, C2, and then, yeah. So here's the idea. So when you write your final solution, x of t, you can just put C1, and then one of the vectors here, so sine t minus cosine t, 2 cosine t, plus C2. I'm just going to use the previous one because pretend we didn't do this one, right? Or any scalar multiple is fine. So this is, you can always skip this step. You can skip this, okay? Which is nice, especially like when you're doing a 3x3 system, which we're going to do in just a second. Okay? Yeah.
you have 2 sine T on the bottom. Does that be cosine as well? For the answer for C2?
I'm taking this, or I took it basically from here, right?
Yeah.
That's this vector.
Oh, okay.
And then this one. So are you wondering why are we just dumping the I?
No.
No? Oh, okay, because I was going to show you that next.
Oh, okay.
What's your question, Jacob?
I just was wondering if we have a coefficient in front of the I that's similar to we just have cosine alpha t.
Yes, I'm going to do one like that later.
Okay.
I just wanted to do a baby example first to not overwhelm you guys. And then here's the main idea, like why are we just ignoring the I? What happened, generally speaking, okay, if I were to just kind of write a rule out, we had x1, which was in the form a plus bi, and we had x2, which was in the form a minus bi, right? Well, I know linear combinations of solutions are solutions, yes? So if I add these together, x1 plus x2, what would I get? Just 2a, which means I have a new solution here. So I could just say a is 1/2 x1 plus x2. So now I have a solution that does not involve any imaginary values, right? No i's are involved. And then similarly, if you did x1 minus x2, what would you get? 2bi, good. And then if I divided by 2i, then I have another solution b, right? Which is x1 minus x2 over 2i. So I can always extract real valued solutions and write my answer in the real valued matrix space to match the fact that the coefficients of the original system were all real. Is that good? Okay, yay. So now we'll do a 3x3, but I'm not going to waste your time showing you that you get scalar multiples out of the additional eigenvector, okay? The book does a very sloppy job of proving it, so I didn't want to traumatize you. You can look at it, though, if you want. Okay, shall we move on? Okay, so find the general solution of the given system. I probably won't tell you on the test, though. They're complex, okay? So we have x prime equals 2, 1, 2, 3, 0, 6, negative 4, 0, 3.
Negative 3.
Oh, thank you. Oh my, that would have ended it for us. Have you caught a mistake and you're like, oh no, I was doing so much homework this weekend. It's like,
Usually if I've done the whole thing,
yeah. Okay, let's go ahead. Let's find our eigenvalues. Do we like this matrix? No.
I mean, you could expand upon the section column, right?
Yeah, column 2 is the one. Going in for that one. There's a few in the homework that are nice that are just like bunch of zeros in it, so don't worry. Negative 4, 0, negative 3 minus lambda. So yeah, let's go down column 2. So just remember this will be minus, plus, and then we don't need the last guy. So I'll have negative 1 times determinant of 3, 6, negative 4, negative 3 minus lambda, minus lambda times, let's see, this is gone, 2 minus lambda, 2, negative 4, negative 3 minus lambda. This is 0, yes? So let's see, 0 is negative, negative 9 minus 3 lambda plus 24 minus lambda times, oh, maybe I shouldn't have multiplied that out. No, we have to, okay. Negative 6 plus lambda squared plus 8, right? 0 times negative 3 lambda, not 0 times, negative times. Here, I'll just make it positive now. Let's move on. 3 lambda minus 15, and then minus lambda cubed minus lambda squared plus 2 minus 2 lambda. So 0 is lambda cubed plus lambda squared minus lambda plus 15. Good? It's odd, which means for sure we have to have one real root, yes? Good. So who's it going to be? Let's just guess. Use our rational roots theorem.
-1.
Bad guess. Guess again.
+1.
No. So we have all of the multiples of 15 over 1, right? Oh, I already wrote plus or minus. So 15, 5, 3, 1. How about -3? You want to try that?
Sure.
Okay. So 1, 1, -1, 15. Hussein, you do it different, huh? Synthetic. On your exam, I saw you did it different. I know they teach it different in places. Okay, -2, 6. It's magic. Good? Okay, so lambda 1, I'll call it -3. Great. And then we have lambda squared minus 2 lambda plus 5 is 0. You can do the quadratic formula, or do you remember the shortcut I taught you guys?
Alpha equals 1, beta equals 2.
Very good. So alpha is 1, beta is 2. So we have lambda is 1 plus or minus 2i. Okay, so we can say lambda 2 is 1 plus 2i, and then lambda 3, 1 minus 2i, just so we keep it all straight. So we have to go through the process, find 2 eigenvectors, right? One for the real, and then just do only one of the complex ones, then you're going to use the complex conjugate and move on. Actually, you don't even need to do that. We're just going to extract the real and imaginary part. Any questions up to here? We're happy? Do you guys like complex numbers? No? Oh my goodness. Okay, here we go. Let's find the eigenvalues. Lambda 1 is -3. Oh, yeah. Thank you. We have the values. We need the vectors. Okay. So, a minus -3 times I. Let's focus. Where's A? 2. Okay. So it'll be 2 plus 3. 1, 2, 3, 3, 6, -4, 0, 0. Yeah? Good? Okay. Well, I know how some of you guys hate fractions with a passion. So let's make our pivot by taking row 3, making it row 1, and dividing by -4 simultaneously. How does that sound? Right? Oh, yes. We knew about this. Don't worry. Unlike the person in the Calc 3 final, whoever they are, they still have not come forward. Okay, so I don't know, this is not legit convention. -1/4 row 3 interchanges with row 1. Do you know what I mean by that? I'm doing 2 things at once. I mean, you don't have to write anything if you don't want to. 1, 0, 0. Does your linear teacher make you write something down? You can just do it. Yeah. I mean, after a while, too, I can look at them and I can just, like, tell, right? You're going to have a row zeros and just move stuff around and, like, oh, that will become a 0. I don't need to actually do it. Yeah. Okay. Good. Then we can use the 1, 0 out the first column. So -3 row 1 plus row 2 is the new row 2. -5 row 1 plus row 3 is the new row 3. 1, 0, 0, 0, 3, 6, 0, 1, 2. And then we're done, right? I would just move row 2 to row 3 and then put a row zeros at the bottom and call it a day. I don't need to see every little step. Please. 1, 0, 0, 0, 1, 2, 0, 0, 0. Okay, if you don't get a row of zeros at the bottom, what happened?
You're wrong.
Very good. Okay, so this times U1, U2. I mean, it's kind of reassuring, right? When it happens, you're like, oh, I'm on the right track. equals 0, 0, 0. Okay. So what can I tell from the first equation? What's u1 equal? 0. And then I have u2 plus 2u3 is 0. So u2 is negative 2u3. So k1, u1 is fixed at 0, and then u2 is negative 2u3. So 0, negative 2, 1 is our corresponding eigenvector. Good? Alternatively, if you had 0, 2, negative 1, that would be acceptable. All right, now let's do one of the complex ones. Just focus. Here we go. Lambda 2 is 1 plus 2i. So we've got a minus 1 plus 2i times I, which would be 2 minus 1 minus 2i, 1, 2. 3 minus 1 minus 2i, 6. Negative 4, 0. Negative 3 minus 1 minus 2i. Okay. So we've got 1 minus 2i, 1, 2, 3, negative 1 minus 2i, 6, negative 4, 0, negative 4 minus 2i. So what do I need to happen?
Probably make the 3 or they all actually involve.
You know, I took row 3 and moved it to row 1 and made the negative 4 a 1. But yeah, you could move the other row as well. I just felt like then at least I already had that 0 in the, you know. But yeah, you have options. Okay, so again, I'm going to take negative 1/4 times row 3 and interchange it with row 1. I'm doing a combo. We're doing two operations at once. So 1, 0. Now this is 1 plus 1/2 I. This I'll leave. 3, negative 1 minus 2i, 6. And then now row 1 is row 3. So 1 minus 2i, 1, 2. Yay! Okay, we're almost there. So negative 3 row 1 plus row 2 is the new row 2. How do I make 1 minus 2i is 0 using the pivot in row 1? What do I need to multiply it by? Perfect. Negative 1 plus 2i, row 1, plus row 3 is my new row 3. Okay. So we have 1, 0, 1 plus 1/2 I. 0, that won't change. Negative 1 minus 2i. Negative 3 row 1 plus row 2 is the new row 2. Okay, let me do that really quick. So negative 3 times 1 plus 1/2 I plus 6 is going to be the new row 2. So that's going to be 3 minus 3/2 I, yeah? Okay. And then negative 1 plus 2i. Row 1 plus row 3 is the new row 3, so that's 0. 0. Okay, let's do this. So negative 1 plus 2i times 1 plus 1/2 I plus 2. I mean, what do we expect it to be?
Negative 2.
Right. What's up, Omar? In the bottom middle? Did I add wrong? Oh, I didn't copy it down? Oh, yeah. You're adding 0 to 1. Thank you, thank you, thank you. Then it's not going to be 0 yet. Okay, let's see what's going to happen. I got too excited. Okay, this is negative 1, right?
Yeah.
Negative 1 minus 1/2 I plus 2i plus I squared, which is minus 1 plus 2. So that all cancels. So I have 2i minus 1/2 I. So that's 3/2 I. Okay. Are we back on track? I was ready for this to be done. I'm so sorry. Thank you, Omar, for keeping us accountable. Okay. So we need to make this a 1. What looks like the least painful way to achieve that? Yes, just interchange 2 rows. Okay, so let's go ahead. Row 2 and row 3, little switcheroo. So we've got, this one's actually ugly. 0, 1, 3 halves I, 0, negative 1 minus 2I, 3 minus 3 halves I. All right, the worst is certainly done, guys. We're almost there. What's the next step? Yes. So we'll take positive 1 plus 2I times row 2 plus row 3. That's my new row 3. And that should do it. Okay. Yeah. It's all zeros now, yeah? So 1, 0, 1 plus 1 half I, 0, 1, 3 halves I, 0, 0, and this better be a 0. Do we want to check or we're good?
No,
We're good. Okay. So this times U1, U2, U3 gives us 0, 0, 0. Okay. So then we'll have U1 equals negative 1 plus 1 half I U3. And U2 equals negative 3 halves I U3. So we could say K2. Let's just make them positive, right? Or should we multiply through by 2?
Yeah.
Negative 2.
Yeah, okay, I'm doing it in 2 steps, but yeah, so let's do 2 plus I, 2 plus I, 3I, and 2. That looks better. Good? Okay, then we don't have to go through. Lambda 3 is 1 minus 2I.
Wouldn't it be negative 2? Yeah.
Do I have the wrong sign? Oh, because I have to change the last one as well. Yeah. Let me check. I didn't simplify it this much when I did it earlier. Yeah, you're right. Thank you. Okay. So then we don't have to do anything else. We can just write K3 is the complex conjugate of K2. So this will be yes, 2 minus I. Very good. And then?
Oh.
Negative 3I, negative 2. Good? Okay. So now, oh, we need another page. Heavens to Betsy. Okay. So we're going to try to write the general solution, but we need to extract the real and the imaginary part out from one of them. So let me just deal with x2. Okay. So the goal is general solution. It should have how many terms? 3, exactly. So we're going to have x equals c1 e to the lambda 1t k1 plus c2 e to the lambda 2t k2 plus c3 e to the lambda 2t k3, right? Okay, so let me just deal with, we already know this one. This one's real. Where? Ah, thank you. Okay. So we already have the first one, right? That's the real one. We already have c1 e to the negative 3t times 0, negative 2, 1. That's done. Now let me go ahead, start playing around with x2, and we'll use Euler's identity. So x2 is e to the, we had 1 plus 2i t times, what was our eigenvector? 2 plus I, 3i, negative 2. Good? Okay, now this is basically your alpha, your beta. So think back to how you wrote your solution to the differential equations in chapter 4, right? So you had e to the alpha t, And then cosine beta t plus I sine beta t times the eigenvector 2 plus I, 3I, negative 2.
Didn't you say to write it on the right-hand side?
I will at the end. Do you want me to put it there now?
I don't care.
I'm just doing it how Euler's identity was for now. And then at the very end, yes, we should move it. You are correct. Okay. So we're going to distribute this through. I'll move it now. So what is this going to be? 2 cosine 2t plus I cosine 2t plus 2I sine 2t plus I squared sine 2t, so minus sine 2t. And then 3I cosine 2t minus 3 sine 2t, negative 2 cosine 2t minus 2I sine 2t times e to the t. So let's separate real from imaginary. So here's real. That's it? I think I'm missing somebody. No?
First line, is that 2 cosine 2 it? Or what, like?
Yeah, what did I write? I think it should have been a t and I wrote an I.
2 cosine
2t. Yeah, I wrote an I and it's a t.
plus 2I sine 2t.
Well, I FOIL different than you.
Oh, okay.
Yeah. I think everybody's there though. All children are accounted for. Yes. Okay. Yeah. So those are the real. This is real. This is real. Perfect. Okay. x2 equals 2 cosine 2t minus sine 2t, negative 3 sine 2t, and negative 2 cosine 2t e to the t plus I times cosine 2t plus 2 sine 2t, 3 cosine 2t, and then negative 2 sine 2t e to the t. Yeah? Very good. I'm checking. I left the fractions last time in the minus, so I just want to make sure. Yeah, we're good. Okay, so that's it. We're going to use those two as basically K2, K3. And you have the same lambda for lambda 2, lambda 3. It's the e to the alpha. Good?
Wait, can you say that one more time?
So this is going to be, when I put the general solution together, we use this for K2, and we use this for K3 in the end. And then e to the lambda 2t is the same as e to the lambda 3t because it's going to be e to the same alpha for the complex conjugates. Let's write it out. So we have, the real one was good, yeah? C1 e to the negative, no, put it at the end. That looks like you're just a savage in the jungle. 0, negative 2, 1, e to the negative 3t plus C2 e to the t. Then we have 2 cosine 2t minus sine 2t, negative 3 sine 2t, negative 2 cosine 2t. Oh, what I just said put it at the end. Plus C3 cosine 2t plus 2 sine 2t, 3 cosine 2t, negative 2 sine 2t. Let me scoot. E to the t. So this, plot. This, plot. Good? Shall we stop there and you just practice some today?
Yeah.
I could do the repeated eigenvalues. Or shall we do that Wednesday?
That's Wednesday.
Let's ease into this, huh?
Remember you saying that they're raised to the same alpha?
Yeah. Because you know how you always have, it's e to the alpha plus bi.
Yeah.
going to
Oh,
be,
the conjugate is the same alpha.
yeah.
Yeah.
Okay, you're good? Oh, I should have put beta, but whatever. So yeah, they're always the same e to the whatever. What? Oh, okay. You know when you use Euler's identity, did I write it out earlier for like...
About how it's e to the it is equal to cosine t plus I sine t.
Yeah, so you have e to the alpha plus beta it. Think back in chapter 4, we did this a bunch, right? When you had your characteristic equation, if it had complex solutions, it's e to the alpha t times cosine beta t plus I sine beta t. So when you have complex conjugates, what changes? All that changes is the plus becomes a minus, right? But the alpha is the same. So that part's going to be the same. And then I showed you guys with the 2x2, when we went through and found the real and imaginary parts for the complex conjugate eigenvalue, eigenvector, we got scalar multiples, right, of the same for the original. So you don't have to go through it again. Isn't that nice? Okay. No one seems excited.
I'm just tired.
Oh, no, you didn't rest?
No.
You had 5, wait, right? Wednesday, Thursday, Friday, Saturday, Sunday. 5 days off?
Yeah.
You didn't sleep?
Thanksgiving
Okay.
break isn't a break.
It's a tease, is what it is. It gives you a taste of the good life, and then we're like, oh no, we have 2 more weeks left. It's like, it almost would be better had we not had it at all and we just powered through and been done in a week. Oh, really? You guys agree?